Hello everyone. In today's lecture, we'll be taking the full longitudinal dynamics of the aircraft and how we can design multiple states at a time. So let us set the problem. Example, we'll take the nonlinear system of the aircraft. So let us consider the nonlinear longitudinal dynamics of an aircraft, which is v dot equal to 1 by m t cos alpha minus t minus g sine gamma, and gamma dot equal to 1 upon mv L plus t sine alpha minus g upon p cos gamma, and theta dot equal to q, and q dot equal to m by, this is the capital M, moment divided by I y. So this is the full longitudinal motion dynamics of an aircraft. And here, maybe there are different, in the different literature, we have different model of the equations, but we are taking this equation, and this is highly nonlinear, and how we can design the nonlinear controls for the system using the feedback linearization based. So here are the parameters. Let me define the parameters for this in these equations. So here v is the airspeed, and gamma is the flight path angle, which is basically gamma equal to theta minus alpha. So here theta is the pitch angle, and q is pitch rate, and t is thrust, is applied to control the longitudinal motion of the system, and d is drag and lift. Here m is the pitching moment, and small m is the mass of the it should be the small m. This is this is the small m, the mass, and this is the moment here, the q dot equation, and small m mass of the aircraft, and I y the principal moment along pitch axis, so moment along each axis, and c is the gravitational constant acceleration. So this is our dynamics equation, which is defined by equation 1. And we are going to design control, which is going to help to propagate the state variables, which is V, gamma, theta, Q. So here we are going to control multiple states at a time for this system. So our objective is design the control to control the airspeed, which is V, pitch angle theta, and pitch rate Q, to track the desired trajectories, which is V dot VDT, the desired airspeed, desired pitch angle, and desired pitch rate. So we have to design a control which is going to help us for this dynamical system to follow the desired airspeed and pitch angle and desired pitch rate. So here we are going to have some simplification for this problem to solve this problem. The solution, we are assuming for simplicity, this is just for assumption to make the problem very simpler. Otherwise, you can go with the as it is, the equation. For simplicity, let us assume the angle of attack is small, and the small angle of attack, alpha, we can come up some simplification for this term, cos alpha and sin alpha. So what you're going to do is, so here you can write cos alpha is assumed to be for small angle, it's assumed to be 1, and sin alpha assumed to be alpha. So here the pitching moment also function of the variables in the system. So so this thing we have covered in our classical controls, the first course, aircraft control system. There we have discussed all this moment and force equations. And the pitching moment M is a function of alpha, Q, and the elevator deflection delta E. So in this case, we can write the total moment due to these parameters. We can write M equal to M naught plus M alpha alpha plus MQ Q plus M D delta E. So these are the values, basically very specific to the particular aircraft, this terminology. So we can get these values from the wind tunnel testing. So these are for the particular aircraft, these values are basically given. And based on that, we can come up this relationship. And here actually this is our control. And based on that, we can come up the M. So while we'll be solving this problem, it will be clear how we are going to do this. So here, where M naught, this is the, we can say, baseline pitching moment. And M alpha pitching moment coefficient due to the angle of attack alpha, and MQ, and this is pitching moment coefficient due to pitch rate Q, and M delta E, this is pitching moment coefficient due to elevator deflection elevated, let me write here, deflection delta E, and delta E is the control input here, control input, and this is nothing but the elevated deflection. Yeah. So now we have to design the control input, this delta E, on this problem. Now, similarly, the lift and drag are the function of alpha and v that we know. So L equal to, we can write half rho v square ACL, so function of alpha, and drag of rho v square ACD, function of alpha. So here basically rho is the yard density, and S is the wing area, and CL alpha, so CL alpha and CD alpha, lift and drag coefficient. Okay. So our as per the problem, what we have as per the objective, so our control objective is the process we are following to solve this problem, the same process we can follow for other dynamical system. So these are the basic examples how we can design the control for this particular system. So if you have another dynamical system in different form, we can follow the same steps. And here actually we are going to use the input-output feedback linearization, what we have done in the last example, in the last lecture. So here the control objective is V should drag V desired velocity, and theta should track theta desired, and Q should track Q desired T. So this is our mission objective. So now let us define a state vector, since you are going to control multiple states in the system. So let us define the state vector. Let us define here like state and output vector. So we are defining X is the state, which is V, gamma, theta, and Q. So these are the states in the system to be controlled, and output vector we are defining by V and theta. So these are the variables coming from the system, and these are the states going to be used to design the control. So here our main motivation, if you remember in the last lecture, we are going to use this output equation to find the control. because we will take the output equation and we'll apply derivation. We'll do the derivations or differentiation for this equation, and we'll come up the derivative of these states, which will be function of the controls. So here, what we're going to do is, let me write here, we need to apply differentiations to the output vector till the control input is appear. So here what we're going to do is we'll take the first variable v, the variable there is two variable in the output, v and theta. So we'll take the first variable. So v will take the derivative of v. So v dot we can write equal to, so what you have given in the problem, v dot equal to this expression, right? So we can write v dot equal to 1 upon m t cos alpha d and minus c sine gamma. So here, if you notice here, we are having control t in the system, because in this equation, if you basically there are two control input. One is the t and another is the delta e. Here, delta e, right? So delta e is going to provide the moment, which is going to control the angle, the pitch rate basically, and our thrust is going to control the velocity of the aircraft. So there is two control inputs for this dynamics. So we need to design these two controls. So in this equation, you can notice the t is appeared. So we can write here, hence thrust appears in v dot. And so we can stop here, right? So now we'll take the second state in the output equation, which is theta. So here we can write theta dot equal to q. So here if you notice here, this moment or the control, which is nothing but the m, actually m is a function of the delta e. So this is not appeared in this equation. The control is not appear. So we have to do, again, we have to take the time derivative. So theta double dot, we can write q dot. So in this case, we can see m equal to I y. So here m is appeared in the output equation. So we can write here the elevator deflection delta E is appeared in theta double dot. So now we can start the feedback linearization concept, what you have done in the last lecture. We can follow the steps and we can find the control laws for T and delta E. So now let us choose E1 and E2 are the new variables, new control inputs for these two equations. Okay, let me define this, the equation number 1, for example. This is equation 1. We hope we have not defined the equations number. Okay, this is 2. This is 2. And this is, for example, 3. Okay, this will 3 equation. Now, this new control inputs U1, U2 for V dot and theta double dot. Okay, so in this case, we can write V dot equal to U1, or we can write In 1 upon m, the same steps for what you have followed in the last lecture, we are following the same steps here also. T cos alpha minus T minus G sine gamma equal to U1, right? And from this equation, we can write T equal to, we can find M U1 plus G sine gamma divided by plus T divided by cos alpha. So here, okay, if you can do also another way. So here basically we can choose v dot equal to u1, and for this you can choose u1 equal to some minus k v maybe. And if you substitute this equation here, it will be stable system, right? So we'll do this part later. So this is how we can find the control t, which is the function of some control, linear control here. This is U1 is a linear control because this is a linear system, right? So now this is how we can design the thrust, which will provide the to the dynamics to control B. Now we'll go to the second equation, sorry, third equation here, this equation. So here we'll design control for theta dot, which is defined by U2. So let's similarly, you can write for equation 3, we can write theta double dot equal to U2. And from this, we can write, in place of theta dot, we can write m divided by Iyy equal to U2. And as you know, already have defined the expression for m in here, this expression. So we can substitute this m in this equation, so we can write here, we can write m naught plus m alpha, alpha plus m q, q plus m delta I, divided by I yy equal to u2. And from this, we can write delta equal to I yy u2 minus m naught minus m alpha and minus mq divided by m delta I. So here we are going to have two controls. One is T and another is the delta I. So delta I is going to provide moment, and that moment going to control the pitch angle and pitch rate, right? Now from this analysis we can write, so now let us design, let us design v dot equal to u1 and theta double dot equal to u2. So for v1 dot, v dot, we can write. So now we have to do here. So we need to design the control for this system. So this is basically a linear system, and we are going to design linear controls for v and linear control for u2 for theta, right? So here we are going to choose this u1, u2 to stabilize. So let me define this, the equation number 4. Okay. Now to stabilize equation 4, u1 and u2 are chosen as, we can write u1 equal to vd dot plus k v1 and vd t minus v. Okay. One thing here, v is actually constant. Okay. At a particular time instant, v is constant. So this is how we can find. And here U2 is designed to be U2 here theta d double dot plus k theta 1. These are proportional control theta d minus theta, and we are designing k theta dot, sorry, I should not, sorry, k theta 2 minus theta d dot minus theta dot. I should not say v is constant because time series. So instead of that, I can explain on this how it is happening here, this particular case. So here basically what you're doing is we have the system here. For example, this is our system. Okay. And let me first define this problem, this equation. Okay, how it is happening. So here we have the desired V here, V D, and we have the controller here, controller, and we have the, from the controller we are getting U1, and this is our plant. So in this case, plant is actually V dot equal to, this is our plant, right? This is our plant, V dot equal to E1. Okay. And this is the output, right? And this is feedback. This is the feedback. This is negative, and this is positive. And this is the output variable actually from this plant is P, right? So now, if you notice here, for this particular, this is the error, right? This is error. So here we can write, so here our error is actually Vd minus V. So based on this, we are actually defining this control. Okay, this is we have done in our modern control techniques. So our this expression U1 actually this we can write. This is the same. This is the control actually. This is the control expression we are getting from this error variable. So this is how we can design control for to control V, and similarly the same way we can define the control input for the theta. So here basically we have used the PD control, and here actually we have used the proportional control. Because we are having here only one state, one derivative part, so that's why this part is coming. And here actually we are going to second order system, and we are using double dot, the desired dynamics of the theta d. And this is the proportional part, and this is the derivative part. So this is how we can come up the linear controls for tracking our time varying and desired values. Okay. So now we can go back to our problems. So if you substitute one more thing here, here k v1 are positive, and k theta 1 and k theta 2 also positive. Now from these two equations, if we substitute in this expression, so we can, not this expression, I shouldn't say, in this expression and this expression, if you substitute, we can come up the control. So now the expression for t, now we can write t equal to, so in place of t, we'll substitute this expression. So here we'll substitute here this one u1. So we can write t equal to vd dot plus k v1 and vd minus v plus G sine gamma plus D divided by cos alpha. And similarly, the expression for U2, we can substitute here. So delta E, the elevated deflection, I y theta d double dot plus k theta 1 theta d minus theta plus k theta 2 theta d dot minus theta minus m naught minus m alpha and m q q, right, divided by whole divided by m delta E. So these are the nonlinear contours. These are the nonlinear contours for our nonlinear system defined here. So that expression t will be, we can fit here, and m in the place of, so here we are going to provide delta E here, we'll get the moment, and that moment going to control these two variable, and here t is going to control these two variable. So this is how we can design the nonlinear controls using feedback linearization technique for this nonlinear systems. So let's stop it here. In the next lecture, we'll have the MATLAB simulation for different system, and we'll wind up this topic. Thank you.